All right, let's look at limits as x gets very, very large. So we're thinking of this as limits at infinity. So as x grows and grows and grows. We'll also look as x approaches negative infinity, where it grows and grows and grows in the negative direction. But for now, let's just stick to infinity. So let's say we have this fairly complicated expression, x cubed plus 2x plus 1 over 3x cubed plus x squared plus 7. Well, to get a feel for the behavior of this, let's plug in some values and see what we get. So I'm going to let x become bigger and bigger and bigger. I'm just picking these values. There's nothing special about 10, 100, 1,000, and 10,000. They're just values that are kind of easy to calculate with. So let's plug in 10 into our function. So we get 10 cubed, that's 1,000, plus 2 times 10, so that's 1,000, plus 20, plus 1, so that's 1,021, over, and let's plug in 10 into this, and you'll see that we get 3,107. And maybe you can kind of see what's going on already with this, but let's do another example of something to plug in to really see what's happening. So let's plug in x equals 100 into this equation, and we get 100 times 100 times 100, so that's 100 times 100 is 10,000, times 100 again is 1,000,000, so we get 1,000,000 plus 200 plus 1. So we get the number in the numerator, 1,201 over, and if we plug that in to the denominator, we get 3,020,007. And you can see, well, this number is very, very close to 1,000,000. This number is very, very close to 3,000,000. We can even do one more. So if I plug in x equals 1,000 into this, what am I going to get? Well, I'm going to get 1,000 cubed, which is 1,000,000,000. And then 2,001 in my numerator. And in my denominator, it's going to be 3,000,000,000, 1,000,000, and 7. So my point here is that, well, this 2,001 bit in the numerator and this 1,000,007 bit in the denominator isn't really affecting what's going on with the size of the number that much. These larger powers of x are dominating. So really, these small powers of x are fairly irrelevant. And we won't bother in plugging 10,000 in. You can try that yourself. But you'll see in all of these expressions, especially as x grows and grows and grows, all of these expressions are getting closer and closer to 1/3. This is like 1,000 over 3,000. This is like 1,000,000 over 3,000,000. This is like 1,000,000,000 over 3,000,000,000. So these guys don't really matter. So we want to say that this limit is 1/3. Now, to do that a little bit precisely, what we can do in some sense is we can factor out the largest power of x in the numerator and denominator. So the largest power of x in both of these is x cubed. And I'm going to even factor it out of the terms where we don't have enough x's. I'll just put it in the denominator for those terms. So I'm going to rewrite this as the limit as x approaches infinity of, I'm going to factor out an x cubed in my numerator first. So that leaves me with 1 in that term. In this term, I only have 1x. So if I factor out 3, then I'm missing 2. So I can write this as 2 over x squared. And you can check that that's correct. If I multiply x cubed by 2 over x squared, I get 2x back. And similarly here, I get 1 over x cubed. And in the denominator, I'm going to factor out that x cubed as well. And I'm going to get 3 plus 1 over x plus 7 over x cubed. Okay. And we can use 2 facts to help us out here. And those facts are as follows. So the limit as x approaches infinity, and in fact we can say plus infinity or minus infinity of any constant, is that constant. Remember, there's no x in here, so if x changes, the constant doesn't change, it remains constant. And the other thing we can use is that the limit as x approaches plus or minus infinity of 1 over x is indeed 0. So as x grows and grows and grows, either positively or negatively, you're going to get a smaller positive or negative number, but it's going to get smaller and smaller and smaller, so you're going to get 0. So we can use those to help us out here. Well, and of course here, we can cancel out these common x cubes. And now, using our limit laws, we can just take the limit of each term in the numerator and each term in the denominator separately. So we have the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 2 over x squared plus the limit as x approaches infinity of 1 over x cubed over the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 7 over x cubed. So, a lot of these just go to 0. In fact, whenever we have a constant over some x's in the denominator, so as x goes to infinity, these denominators are going to go to infinity. So these, just like 1 over x, all go to 0. So we'll mark that off. That goes to 0. That goes to 0. That goes to 0. That goes to 0. Again, picture what happens as x grows. As x grows, say you plug in 10, you'd get 2 over 100. If you plug in 100, you get 2 over 10,000. If you plug in 1,000, you get 2 over 1,000,000. If you plug in 10,000, you're going to get 2 over 100 million, etc. So you get smaller and smaller fractions. So this eventually goes to 0 as x goes to infinity. And a similar argument can be made for all of these guys. So all we're left with is the limit as x approaches infinity of 1, which is 1, over the limit as x approaches infinity of 3, which is 3. So the limit here is 1/3. And we kind of developed a nice technique here to find these limits. We can just factor out that largest power of x in the numerator and denominator and find our limit. Let's look at some more examples. So here we have the limit as x approaches infinity of this. So let's do that same thing. The largest power of x in the numerator is squared. The largest power of x in the denominator is x to the fourth. So let's take those out. So we get the limit as x approaches infinity of x squared, and I'm left with 1 plus 2 over x. Again, you can see that x squared times 2 over x is 2x. And then we'll take x to the fourth out in the denominator. So we get x to the fourth times 4 minus 1 over x cubed plus 1 over x to the fourth. And you can see here, we can't cancel off all of the x's in this case. We can cancel off all of them on top. But down the bottom, we can only cancel off 2 of them. So, again, let's do this the long way. So, this is going to be equal to the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 2 over x, so that's our numerator. And I will say, eventually, after we do a couple of examples, I'll stop kind of doing this the long way, and we can just look at this and saying this is a 1, this will go to 0 as x approaches infinity, etc. Okay, and here, we're left with the limit as x approaches infinity of x squared times the limit as x approaches infinity. I'll just write this whole thing as 4 minus 1 over x cubed plus 1 over x to the fourth. So you can see that this whole thing, using techniques from before, this is going to approach 4, since we have 4 minus, this is going to be 1 over infinity, which is 0, and 1 over infinity, which is 0. And when I say is 0, it's not exactly 0. I'm saying as x approaches infinity, this expression approaches 0. So I'm just using some loose language there. And up top, we kind of get that same idea. So this whole thing approaches 1. But the whole thing is we have the following now. We have that this equals 2. We have 1 over the limit as x, I'll write it like this, limit as x approaches infinity of x squared times 1/4. But we know as x grows, x squared grows as well. So this becomes infinity. And thus, this limit goes to infinity. So we have 1 over infinity, which is like 0. So this whole thing approaches 0 times 1/4, which is 0. Again, we're thinking of 1 over something that approaches infinity approaching 0. So we get 0 times 1/4 equals 0. And it wasn't really important the power of x that was out here. If we just had 1x, this would approach infinity. If we had 2x's or 3x's or any number of x's, it would approach infinity. So what that's saying is that if the largest power of x in the denominator is larger than the largest power of x in the numerator, we're going to get 0. And that kind of makes sense. Our denominator will grow much, much faster than our numerator. A good exercise for you guys is put in some values just like we did in the previous example. Let's do x and f of x. Plug in 10, 100, and 1,000 and see what numbers you get when you plug in those into our function. Let's look at one more. Let's do a limit to negative infinity now. X approaches negative infinity. So let's do x squared minus x plus 1 over 3x plus 7. And let's do that same idea. In fact, you know what? I'm going to change this a little bit. I'm going to make this x to the 6th instead of x squared. Whatever, it doesn't really matter. So again, I'm going to take out the highest power of x in the numerator and denominator, but I'm going to have to be a little bit careful here. So the highest power is x to the 6th. So this is going to be 1 minus 1 over x to the 5th plus 1 over x to the 6th over, and I'll take out the highest power of x in the denominator now, which is just 1. So we get x to the 1, and we're going to get 3 plus 7 over x. Now, from what we did before, you can see, well, these guys, this is going to approach 1 since it's a constant. This is going to approach 0. This is going to approach 0. This is going to approach 3. This is going to approach 0. So the numerator is going to approach 1 as x approaches negative infinity. And again, it doesn't really matter if x grows infinitely large or infinitely small. In the denominator, the whole thing will approach 0. And same thing down here, same idea. This will approach 3. And we can cancel off our x with one of the x's here. So we can rewrite this as the limit as x approaches negative infinity. And now we have x to the 5th times, and what do we have here? We've already kind of worked out the limit there. So the limit of the numerator that's left over besides the x to the 5th was 1, and the denominator limit was 3. So obviously the 1/3 isn't going to really matter with what's going on here. We just have x to the 5th. But we have to be careful. So as x approaches negative infinity, we have numbers that are negative getting raised to the 5th power. So here we get negative times negative times negative times negative times negative. So that's an odd number of negatives since we have an odd power. So our numbers here are going to be negative. So as x approaches negative infinity, x to the 5th approaches negative infinity. So this is going to be negative infinity times 1/3, which is still negative infinity. If instead we had the problem, the limit as x approaches negative infinity of x squared, well, here we have approaching negative infinity, but a negative times a negative gives us a positive since we're taking x and we're multiplying it by itself twice. So we always get positive numbers here. So this is going to approach positive infinity. So when you have a negative infinity, just be careful of what the sign of your limit is going to be. So here we have it approach infinity since we have an even power of x. Here we have it approach negative infinity since we have an odd power of x. So just be careful. You can just think about it. You don't really need a rule to memorize. Just think that, hey, we're multiplying an odd number of negative numbers together, so our answer is going to be negative. Here we're multiplying an even number of negative numbers together, so our answer is going to be positive. From the previous discussion, we can talk about a rule that we can glean here. And in some sense, we've almost proved this. But we can glean from that previous discussion that the limit really only depends on what the highest power of the numerator and denominator polynomial was. The first example had that the highest degree was 3 in both the numerator and denominator, so they had an equal degree. And remember, the degree is just the largest power in your polynomial. So if we had x cubed being the largest power, our degree would be 3. If it was x squared, our degree would be 2, etc. So here we have if the largest power has the same degree, same exponent, then the limit is going to be the coefficients of those terms. So I'm using a's and b's to be the coefficients for my polynomial. So it's just the coefficient of the top one divided by the coefficient of the bottom one. If the top polynomial has a larger degree, then the limit as x approaches infinity is going to be infinity. And if the bottom polynomial has a larger degree, then the limit is going to be 0. And with negative infinity, it's almost the exact same. I'll just update this in red for negative infinity. The only thing we have to be careful about is whether the limit in the case where the top polynomial has a larger degree, whether that's going to be plus or minus infinity, let's say depending on n minus m is odd, you'll get negative, or even, you'll get positive. But you don't really need to remember that rule. You can just kind of figure that out as you go, whether you're going to get plus or minus infinity. So, for example, if we had something along the lines of the limit as x approaches negative infinity of, let's do 3x to the 5th minus 4x squared plus 7 over 2x to the 5th minus x to the 4th plus x cubed minus 29x squared plus x plus 1, for example. Well, all we need to look at is the degree of the numerator and denominator. Here we find that they have the same degree, degree 5, so the limit is just going to be the ratio of the coefficients. an, in this case that's 3, and bm, in that case that's 2. So our limit is going to be 3 halves. Let's do a few more examples, especially ones involving square roots, where you have to be just a little bit careful. Okay, so we're going to do something that's very similar here. We'll start with the positive case, but then we'll move to the negative case because there is a real difference, and you really have to be careful here. And I'll explain why in just a second. So, but if we're just thinking kind of in general, the largest term in the numerator, the dominating term, is this square root of 3x squared. This 1 is kind of irrelevant as x gets larger and larger and larger. That 1 just becomes so small, it's such a small part of the numerator, it doesn't really matter. And in the denominator, our largest term is just this x here. So I'm thinking about the largest term really being the square root of 3x squared in the numerator, which is like something like square root 3 times x, if we're forgetting about this 1. So I'm thinking that this should be like the case where we have a polynomial up top and bottom. We're just looking at the highest powers and they match, because the square root of 3x squared, this would be like having the highest power be, well, the square root of x squared is just x. So it's like having x being the dominating term in both the numerator and denominator. So what I'm going to do is I'm going to take out a square root of the highest power in the numerator. So I'm going to write this now. I'll do it in 2 steps. This is the same thing as the limit as x approaches infinity. Again, I'm leaving a little space so we can do negative infinity in a second. And I'm going to write this as the square root of, I'll take out an x squared, and I'm left with 3 plus 1 over x squared in the numerator. And in the denominator, I'm going to take out that x term. So I'm left with 1 minus 1 over x. And now, well, we can split up that square root. So let's go ahead and do that. So this is going to be the square root of, I need to write my limit in here because I didn't take the limit yet. So I need to tell people that I'm still interested in the limit of this expression. So keep that there. So I'll write this as the square root of x squared times the square root of 3 plus 1 over x squared over x times this 1 minus 1 over x. And here's the important bit. Remember that the square root of x squared, well, what does that equal? A lot of people think that equals x. And that's not always true. It's true for positive values. If I plug in 10, say, I get the square root of 10 squared, which is the square root of 100, which is 10. So it works for positive values. But for negative values, if I plug in negative 10 squared, well, I get the square root of negative 10 times negative 10 is 100, and the square root of 100 is 10. So when I plug in negative values, I get negative what I started with. I can write it as negative 10. So I have to be careful whether my x values that I'm plugging into a square root, whether they're positive or negative when I'm canceling these out. When we're approaching positive infinity, well, we can just say this is like x. So let's go ahead and do that. The square root of x squared is just like x. I'll write it as the limit as x approaches infinity of x, because we're in this case here when it's positive. So we have x times the square root of 3 plus 1 over x squared over x times 1 minus 1 over x. And of course, our x's cancel. And we're left with the limit as x approaches, I'll make a little room here, infinity of square root 3 plus 1 over x squared over 1 minus 1 over x. And remember, I'm not going to do this formally, but as x gets bigger and bigger and bigger, 1 over x gets smaller and smaller and smaller, so that goes to 0. And this here also goes to 0, so that will go to 0. This will go to 0. So this is like the square root of 3 plus 0 over 1 minus 0. So we get square root 3 over 1, or just square root 3. So as we approach infinity, we get square root 3. But let's think about what happens as we approach negative infinity. Well, all of this work is going to stay the same. Let me write in my negatives here. There's only one spot that'll be a little bit different. And it's this argument that I was talking about here. When we're taking the square root of x squared and we're putting in negative values, well, then we're going to get a negative x here instead. Remember, if we're taking the square root of negative 10 squared, we end up with negative 10. So to account for that, we need to say that this is negative x squared since we're plugging in negative values. Or sorry, negative x since we're plugging in negative values. And in that case, we're just going to introduce a negative sign here and here and here. So the answer as x approaches negative infinity is square root 3. So what is this going to look like? We can just graph this really quickly. We know we have an asymptote at x equals 1. We could take the limit as x approaches 1 from the left and the right. So let me just do a little sketch here. We're going to have a vertical asymptote where it approaches either negative infinity or infinity. And you can check from the right, it approaches infinity, and from the left, it approaches negative infinity. So we're going to get something like that. But there's going to be a little bit different behavior as we approach infinity and negative infinity. Remember, as we approached infinity, so without that negative, we approached positive square root 3. So we have a horizontal asymptote at, here's our line at square root 3. So our function's going to look like that. But as we approached negative infinity, we approached negative square root 3. So our function is going to approach negative square root 3. So we have this kind of gap where there's absolutely no y values achieved by our function. And that's kind of very interesting. We have a function that's defined everywhere except at x minus 1, but there's a whole whack of y values, anything between negative square root 3 and square root 3, that are never hit by this function. There's no way to get y equals 0, y equals 1, anything like that, anything between square root 3 and negative square root 3. So just be careful when you're doing limit problems at infinity, especially when you have a minus infinity there, that you take into account the negative behavior of it. Like in that previous example, when it was approaching negative infinity, we had a larger power in the numerator. We had to determine whether we were going to approach negative infinity or positive infinity. And in this example, when you're dealing with kind of square roots of x squared or similar terms than that, make sure that you're taking into account what's happening, that you're going to get negative those values. So just be careful in aspects like that. I want to talk about a little bit of a warning, if you will, when you're dealing with infinite limits. We'll do an example after this, but kind of the arithmetic of infinity is kind of weird in a lot of cases. In some cases, it isn't. I'm going to call c some sort of constant, so it's just a real number. If we're taking two limits and the limits are infinity, and we add them together, well, if we take a very large quantity and we add a very large quantity, we get something very large. So we're thinking of this. I'm gonna write equals. It's not quite exact, but for our purposes, it's fine. Infinity plus infinity equals infinity. Again, infinity, they're not real numbers here. It's a concept, but hopefully it's clear what's happening. Infinity plus infinity is infinity. Adding large quantities gives you another large quantity. Infinity plus some real number, well, or even minus a real number, it doesn't really matter. Again, this is infinitely large, and you can add or subtract anything fixed to it, and you're going to get, again, something really large. Since this is fixed, infinity is always, in some sense, bigger than any fixed number, so you still get infinity. These two cases are no problem. However, if we have infinity minus infinity, well, we have a really large quantity and we're taking away another really large quantity. What does that mean? And the answer is, this is an undetermined thing. We don't know. We need to do some more work to figure this out. And it's not that it's bad, it's just a little bit more work. But just be careful in situations like that. Let me show you why with a couple of examples here. So let's call f of x 1 over x squared. Let's call g of x 2 over x squared. And let's call h of x 1 over x squared minus 1. And as a little bit of an exercise, you guys should be able to see that the limit as x approaches 0 of the first guy is positive infinity. The limit as x approaches 0 of the second guy here, is also positive infinity. And the limit as x approaches 0 of the third guy, h of x, is also infinity. I'll leave that as just a small exercise for you guys to practice taking infinite limits. And kind of the key for this is just making sure that you approach 0 from both the left and the right, and the type of infinity matches up. So let's look at the limit as x approaches 0 of f of x minus g of x. So this limit would be infinity, and this limit would be infinity. So you'd have infinity minus infinity, and you'd think, well, what does that mean? But we can simplify that. We have 1 over x squared, that's f of x, minus 2 over x squared. So we're left with the limit as x approaches 0 of negative 1 over x squared, which is indeed negative infinity. So we came up with an example where we're of the form infinity over infinity, and we get negative infinity. Let's look at the limit as x approaches 0 of f of x minus h of x. So this one's pretty easy. We get 1 minus x squared minus 1 minus x squared minus 1. So we're going to get 1 minus x squared minus 1 minus x squared plus 1. If we subtract these, the 1 minus x squareds are going to cancel. So this is just the limit as x approaches 0 of 1, which is, of course, 1. And finally, let's do something where we get positive infinity. I'm going to erase this guy here to make a little bit of room. So we get the limit. Let's do g of x minus h of x. So here we're going to get 2 over x squared minus 1 over x squared minus 1. So if we do that simplification, we're going to get the limit as x approaches 0 of 1 over x squared minus, or sorry, not minus 1, plus 1. And this is, of course, positive infinity. Again, this is of the form infinity minus infinity if we're going to take these limits separately. So the idea is whenever you see infinity minus infinity, you're thinking a little more simplification has to be done. And also, it kind of clues you in about the limit laws that we talked about a few lectures ago. Remember, those limit laws worked when the limits were real numbers. If your limits are infinity or minus infinity, then you can't use those limit laws in the same way. You have to be a little more careful. So just a little heads up, if you're of the form infinity minus infinity, you have to do a little more work to determine the limit. Let's let's look at one final problem here. So we looked at the limit of sine x over x as x approached 0. Let's look at sine x over x as x approaches. We'll do positive infinity, but negative infinity's argument will be kind of the exact same. Now, a good idea is just to think about what's going on in terms of the numerator and denominator. The denominator is easy. As x approaches infinity, x approaches infinity. X gets really large. But remember, sine is a bounded function. So sine is always between -1 and 1. So we're thinking this numerator can never catch up to the size of the denominator. This is going to behave kind of at the most extremes like 1 over x and -1 over x. So this is bounded by some constants. This grows to infinity, so this is going to operate like constant over x, which is, as x approaches infinity, goes to 0. So we're thinking that the denominator grows way faster than the numerator. In fact, this doesn't grow. This just oscillates between 1 and -1. So this is going to approach 0. But let's see if we can show that a little more formally. And we're going to do that by using the squeeze theorem here. So kind of the same idea. We know sine x is bounded by -1 and 1. So we have some bounds to develop some squeezing functions. So if we divide everything by x, well, let's go ahead and do it. So I'm going to write down -1 is less than or equal to sine of x is less than or equal to 1. The y-coordinates of points on the unit circle are always between -1 and 1. We'll divide everything by x. And now note that the limit as x approaches infinity of -1 over x, well, that's going to be 0. And the limit as x approaches infinity of +1 over x is also 0. So we have these squeezing functions for sine x over x. And those squeezing functions have the same limit as x approaches infinity. So we can say that by the squeeze theorem, we have that the limit as x approaches infinity of sine of x over x equals 0. Those squeezing functions have the same limit, so the function that's being squeezed by them must also have the same limit. And if I was to sketch this, I'm just going to kind of sketch it over towards infinity. I'm not going to care about what happens towards 0. If I sketch this, well, it's going to oscillate between positive and negative, but the denominator is going to make the numbers smaller and smaller in magnitude, so it's going to go towards 0. So my function is going to look something like that. And there's another example of the squeeze theorem. Again, whenever you have bounds, or you can invent bounds, and with trig functions, you're always in a good case to make some bounds. These types of functions are great candidates to try some squeeze theorem techniques.